In the name of God, the compassionate, the merciful, Chapter 4, Constitutive Relations, Part 4. In this part, we are going to talk about another example, which is a combined tension torsion of a thin wall tube. Now, thin wall tubes, we had an example in the previous chapter. When we considered the yield criteria, we solved a similar problem. But as you may recall, this kind of loading is for testing and finding out the experimental data for the yield criteria. In here, as you can see, we have a thin wall tube and we have axial as well as torsional loading. Now X, Y, Z directions are shown here, and these are the only stresses acting on an element on the wall of the thin wall tube. Okay, so we have sigma XX, because that's the normal stress, and the torsional loading only applies shear load sigma XY. Now this was you may recall in chapter 2 we had this Taylor-Queeny tests on thin wall tubes in order to get the experimental data for the yield criteria and verify the yield criteria. So as we said, the only stresses are sigma XX and sigma XY, and we use the Prandtl-Ross equations, which we had before. We had these equations before, and in the previous examples we didn't have the shear strain, but here we have the shear strain epsilon XY. Clearly epsilon sigma ZZ and sigma YY are 0, and we have only sigma XY and sigma XX. So we get these values like here. If we put here sigma XX, here 0 and here 0, so we get 1 over E d sigma XX, that is 0, 2 over 3 d lambda sigma XX, and that is 0. And for d epsilon YY and ZZ, obviously the sigma ZZ is 0 and sigma ZZ is 0 here. So we just have sigma XX, and these two become equal like that. And from here we have obviously, because sigma XY exists, so the same equation. So these are the final equation for the Prandtl-Ross, and I've written them here again. Now consider the case where the tube is twisted, because this torsional loading and axial loading we have, we can increase either of them or keep one of them constant and increase the other one until we reach the yield point. In this problem, like before, we want to find the elastic plastic solution. So here, as it says, we consider the case where the tube is twisted up to the yield point. So let us consider that we increase the torsional loading until the tube reaches the yield point. Okay, torsion is then halted and tension is applied, and after we applied the torsion and reached the yield point, we stop the loading and apply this load. I mean, we stop the torsional loading and applied the axial load and increase the axial load. Okay, tension is applied, holding the angle of twist constant, so that we don't increase the torsional loading anymore. We stop the torsional loading. Okay, so if we stop the torsional loading and start the axial loading, because we are in the plastic region, we don't get any further strains due to the torsion because we have stopped the torsion. We get strains, but the strain is due to this axial load. That's why we have put d epsilon xy equal to 0, because we have said that we have halted the torsion, stopped the torsional loading. If we stop the torsional loading, no shear stress, okay? No shear strain. When we have no shear strain, of course we have no shear stress because we are in the plastic region and everything is freezed, you know? We have deformation in the plastic region, but it's freezed because it's plastic deformation. And because we are not applying any more torsional loading, so we don't get any shear stresses and we don't get any shear strains. The only strain and stress is due to this load which is applied in the axial direction. d epsilon xs is equal to 1 over d sigma, because here we have put instead of sigma xx sigma, and in here instead of sigma xy we have put tau. So from this equation, because we have d epsilon x equal to 0, then we could get this d lambda. We can obtain d lambda from here and put it there and get d epsilon xx. Okay, so that we have to do some manipulation here between these equations and this one to get that one. Now if we take the von Mises criterion, which is this one, okay, for this kind of loading, if you put in the von Mises criteria the stresses, you get this. Assuming perfect plasticity. Perfect plasticity means that once we enter the plastic region, the stress does not increase. We don't have any strain hardening. For a constant stress, we get deformation. So if we take the perfect plasticity, then d epsilon xx, this formula becomes this, due to, because we have this d tau over tau, so we could get it from here. This d tau over tau, we get it from here, substitute here, and you get this one, okay? So we have d epsilon xx in terms of sigma and y and d sigma, and therefore we can use this relationship to integrate it, okay? So if we integrate this expression, we get this, which gives us the epsilon xx, okay? That is for perfectly plastic material, not for strain hardening material. Okay, we could get another relationship for strain hardening material, but here we have assumed a perfectly plastic material. And if we plot this epsilon xx and sigma, we get something like that. That is the curve. As you can see here, it goes exponential, because once this sigma over y reaches, in fact sigma reaches the yield stress, you know, it goes up like that because it's a rigid plastic. One thing to note here is that with this formula that we had, this is the yield criteria, von Mises yield criteria for this loading. As sigma increases, if you look at this and look at this curve also, as sigma increases rapidly to its limiting value y, see, as we said that the sigma reaches the limiting value y and it does not increase anymore, so it is constant, but we have this deformation. So we have constant load but increasing deformation. That is what rigid plastic means. So it says that, note that as sigma reaches y and the curve goes like that, tau decreases from its yield value of y over root 3 to 0. If you put sigma equal to 0, you get tau equal to y over root 3, and if you put tau sigma equal to y, you get tau equal to 0. So that's what it means, as sigma increases to y, tau decreases to 0, from y over root 3 to 0, because when sigma is 0, we have only torsion. Okay, we have only torsion. That's why tau is equal to y over 3 at yield, because when we increase only the torsional loading, we don't have any normal stress here. We reach the yield point, and yield point only is due to shear stress, tau, and we get this tau equal to y over root 3, where sigma is 0. But when we increase sigma from 0 to y, then the yield, the shear stress goes to 0, because here we have stopped the torsional loading. Okay. Here just want to show you another flow rule, as shown here. The flow rule used in the preceding application was the Prandtl-Ross rule. Also we introduced the Levi-Mises, which is a special case of Prandtl-Ross, and there are many other flow rules that have been proposed in many publications and have been used as constitutive relations. Another one is this Tresca flow rule, which is very simple. If sigma 1 greater than sigma 2, sigma 3, then we have the epsilon 1 p, which is the plastic strain, is d lambda, and the epsilon 3 p is minus d lambda, and the epsilon 2 is 0. Okay, so that is another flow rule, which is for a plane strain case.